Good morning, everyone. I'm Daniel Coca. I'm the head of the Automatic Control and Systems Engineering Department and also a member of the governing board of DAFNI. For those of you who may not know what DAFNI is, the data analytics facility for national infrastructure is 8 million investment by the UK Collaboratorium for Research of Infrastructure in the cities. And it's aimed to provide essentially world-leading research infrastructure for infrastructure research. Now, what it actually provides is compute capability, data and models database, collaborative modeling and simulation framework, as well as analytics and visualization tools. Now, in recent years, we can say DAFNI has emerged as an ideal platform for digital twin research and development. And this event is part of a pilot project that's funded by DAFNI Champions Initiative and is aimed at exploring the DAFNI digital twin capability. The aim of the workshop today is really to showcase what DAFNI has to offer and how it fits within the current research landscape, with a focus on its current and future capability to support digital twin research. And to that end, we assemble a program that includes technical presentations and demos that illustrate DAFNI capability, results of our pilot project, as well as talks by people involved in managing the National Digital Twin Program and the development of digital twins for aviation, fleets, and urban infrastructure. We also have time for questions and answer sessions and discussions and feedback. Now, I'm going to start. I thought that's a good idea to start by introducing the concept of digital twin, because I thought that not everybody may be familiar. So it's really a top-down introduction. I'm trying just to share the screen with you now. Let's see. A minute. Okay. So, Marian, is that visible?
Yes, looks good.
Okay. So I thought I'll go through setting the scene by trying to answer a few basic questions, and probably the one we should start with is what is a digital twin? And the reason I'm starting with this is that we have so many different definitions. Depending on who you talk to, they have a different view what a digital twin is. So I've summarized here a few definitions from some major industry players, national center, and an academic definition. So in essence, you can see that all what they have in common is that digital twin is some sort of virtual representation of a physical system. And the most important characteristic of the digital twin is that it's using actually real-time data to update the digital twin model. And this model then is used to enable understanding, management of the system itself. Now, the key aspect of digital twin, or the key property, the fact that it's connected with the real system in real time, is not always apparent. So some researchers think that just having a model of a system, it's enough to have a digital twin. And this is an important point to make, that this is having a model of a system, because we use model when we design systems. That is not a digital twin. In essence, a model becomes a digital twin when it follows the system in its life cycle, and it mimics its operation in real time. So if I were to look at what you need to implement now a digital twin, what we really need is historical and real-time data storage. And this is what DAFNI National Infrastructure Database offers. So I'm trying to make a parallel with what the digital twin infrastructure has to offer and what actually DAFNI has implemented already. Because digital twins rely on huge amounts of historical data and information processing. You also need a large-scale sensor network to collect this data in real time. And to some extent, urban observatories provide that facility. Obviously, you need to link our urban observatory with DAFNI in order to provide a real-time update of the digital twin. You need a compute capability, and that has to be a high-performance computer because digital twins require a lot of information processing. And this is, again, what DAFNI high performance and cloud capability provides. Collaborative modeling, platform for modeling. So a digital twin is not something you will be developed overnight. So it's a collaborative effort. You need to bring together models developed by different teams, and these models have to operate seamlessly, have to be possible. It has to be possible to integrate these models in a seamless fashion. And again, this is what the DAFNI modeling service offers by essentially putting models in containers and ensuring they all operate using the common standards. So essentially, the framework is model agnostic. And to get value out of these models, you need analysis and visualization tools. You need to interpret, analyze the model. You need to understand the properties of the system that you're monitoring, and obviously you need tools to make decisions based on this information. Ultimately, and finally, you need to have a secure environment because a lot of the time this data that you're using is commercially sensitive, and again, DAFNI offers a security service to ensure this. Now, if I were to summarize what the digital twin is, probably this is a diagram that illustrates it. So on one hand, you have the hardware, the compute layer on which the models, where the models are stored, and you're running the analytics and artificial intelligence there. But most importantly, you have this connection with the real world. And I've portrayed here 3 loops. So the one loop is the sensing one, essentially bringing data into the digital twin in order to update your models and also for analysis purposes. You have the supervision loop, essentially the user who is using the insights provided in the digital twin is making decision in relation to the real system. And ultimately in the future, essentially you want to remove the supervisory role or take over some of the roles and give them to the analytics and AI layer who should provide autonomous decision making through this actuation loop. So this is really a simplistic view of digital twin, but I think it captured the key elements, what you expect the digital twin to have in place. As an example, I can give you we are building a digital twin in Sheffield. This is an education digital twin, and it's around the cyber physical lab. It's Festo that makes this system. You can see him in this lab on the left here. Now, in parallel, we have built a model of the system, and we connected it with the system in real time, and we started modeling the system, as you can see shortly. And I have here a video that I'm only going to show you probably a small section of it. So this is our digital twin running in parallel with the system. So the moment is synchronized with data provided by the sensors. But obviously we have more work to do in terms of exploiting the data that is being collected for analysis and insights, as well as control. And I'm moving faster because of time. Now, one of the questions people ask is, what should we expect from a digital twin? How far can we take a digital twin? So I've tried to articulate sort of expectations in terms of functionality and for a digital twin, and look at how a digital twin will evolve as it gets refined. And because at the moment we can't expect to get a digital twin in its ideal form, at least we want to look at what is the minimum functionality that we should expect, and this is what I call the basics digital twin. And I would say that the way you can assess the digital twin maturity is in terms of how much trust you put in letting the digital twin make decisions for you, and that is reflected by obviously the quality of the models, ability to collect data and update the model in real time, capabilities of making autonomous decision making, and what algorithms it implements in terms of data assimilation, analytics and visualization. So this is what I expect to see from a very basic digital twin, and probably the one that we are implementing in as a digital twin lab that has many of these characteristics. Now moving to what I call the level 2, but these levels are not industry set by industry. These are sort of artificial levels. I think you can probably introduce intermediate level of maturity if you want. I think it's the digital twin that can be trusted to and used for advanced reporting, analysis, and forecasting. I think the use of high fidelity model is one of the characteristics. Essentially, it's got standard predefined decision-making capabilities. So this is pre-programmed and it's not evolving in the future. It's not evolving, it's not changing. It's got advanced data assimilation capability, and this is in order to ensure convergence within the sampling time as well as accuracy as well. And it has advanced predictive analytics, and probably a digital twin that later on one of my colleagues will present for the aviation fleet management, probably that has this level, if not higher. Now moving higher on the scale, you have digital twins that I would expect to support strategic decision making, and this will have models that really multi-fidelity hybrid models. When I call multi-fidelity is that you have low fidelity models for fast optimization as well as higher fidelity models for other levels of decision making. And these models are of the complex cyber-physical systems and not just of a subsystem. So there are high models of high level of complexity. It has real-time operation, and it also has a more advanced adaptive control decision making. So essentially, this digital twin will have the learning ability embedded within it. This digital twins will probably also describe systems that are distributed in space, so that we will have also advanced spatial temporal analytics and visualization, and probably that's what an infrastructure twin of a national motorway, for example, system will have to achieve. And if we go further, I would say that the level 4, and this not necessarily the top level, this is a digital twin that can be trusted for autonomous decision making, and this will have dynamic, multi-scale, multi-domain, multi-system models, and it can be seen as also as a federated digital twin. So essentially an assemblage of digital twins that of lower complexity, but they are connected together and operate in synchronicity. Again, it has real-time operation, a higher level of autonomy, state-of-the-art analytics and visualization, and as well as artificial intelligence, machine learning capability. Now, to stop in terms of how far can we go, I've recently read this fantastic book by Arthur C. Clarke, The City and the Star, which I recommend to you. And this is probably 1956 vision of a smart city. And I think that the digital twin portrayed in there, which is a computer that actually controls the city, in its entirety, manages all the operations. I think that's probably as far as we can hope to get in the future. And in terms of applications, I think these are just a list of applications and benefits that the digital twin should provide, and probably this go from what the from lower levels to higher levels of complexity. So as a basic digital twin, we provide a representation, simple representation of operational data, analysis of historical trends and potential causes of portfolio deterioration. We can get more, provide more support for decision making, optimization of day-to-day operations, and going further in terms of identifying abnormal behaviors, reducing downtime, as you can see, up to essentially going to higher level of autonomy in terms of identifying, recommending new intervention and actions, and since reducing the dependence on the human operators with an aim to enhance the safety and reduce operator error. I'm sure you'll see later on some more examples of the benefits of digital twins. But in a nutshell, this is what I wanted to cover. So just to take you through the basic definitions, applications, and architectures of digital twins, as well as a way of maybe we can assess the maturity level and set our expectations. I'll stop here, Marion.
Thank you.
Thank you very much.
Thank you.